Alright, let's do a debrief for reaction kinetics in class exercise 1. The first question asks you for the units for the rate constant K for a first order reaction. So let's say the first order reaction, we can write the Rate's law as rate is equals to K A to the power of 1. The units for rates is usually moles per dm cube per second, and the units for concentration is usually moles per dm cube. Okay, so if you look at both left and right, the units for concentration cancel off, and then therefore the units for rate constant will be per second. So in that case, I will choose option A. Okay, so this can be done quite fast, or if some of you want to commit to memory, you can just memorize, but suggestion would be if you can derive it, you can just derive it quickly. Okay, the next question will be question 2. So you were told that there are two radioactive isotopes G and H, half-life given to be 5 minutes and 15 minutes respectively. An experiment begins with 4 times as many atoms of G than H. So given that the radioactive decay is a first order reaction, how long will it be before the number of atoms left equals the number of atoms of H left? Okay, so this particular question, you can do it fast, or you can do it through mathematics. It's really dependent on you. Let me just show you a quick way of doing this. Okay, so we will first be writing out G here and H. Okay, this question can be solved easily, or you can use the mathematics to solve it. So I'm going to show you both methods. The mathematics method is probably a little bit more demanding. Yep, but nonetheless, I'm going to show you. Okay, so I'm going to show you the easier method first. Okay, so I'm going to write down G here and then H. Okay, so you were told that the number of atoms of G is 4 times that of H. So if we let H be X, G will be 4x. Okay, so let us see whether after we go through several half-life, whether the number of atoms can match. Okay, so let's just try. So for G, after one half-life, I will end up with 2x. After another half-life, I will end up with x, and after the third half-life, I'll end up with 2x. Okay, for H, after one half-life, I'll end up with half x. Yep, so it seems that the number actually match between the two, because both of them will reach half x. Okay, so if you just count the half-life, you have 3 for G. So in the case of G, it will be 5 minutes, 5 minutes, and 5 minutes. And in the case of H, it will be 15 minutes. Yeah, so in that case, I will pick the option C, which is 15 minutes. There is a common misconception that students have, which is to actually pick 10 minutes. The argument that the student have would be, oh, you see, G, right, after 2 half-life, I reach X. So that's 10 minutes, right? Then isn't that the same amount of H that I have at the start? But the problem is, after 10 minutes, H will have decayed somewhere between 100% to 50%. Maybe 2/3 way lah. So it shouldn't be looked at as though when 15 minutes is up, then suddenly X becomes 2X. It should be viewed as a consecutive process, otherwise known as an exponential decay. So that is why the mathematical method is actually clearer for students. Of course, you don't need it to do question 2 lah, because question 2 can be solved quite easily because they give you beautiful numbers. Yeah, so for those of you interested in the mathematical method, I can show you over, in the next blank sheet. Okay, so for the mathematical method, I think first of all we need to get some parameters right. Okay, so we know that T half is equals to ln 2 over K for first order kinetics. Okay, so therefore K is equals to ln 2 over T half. Okay, and for first order kinetics, we learned that it's actually an exponential decay, lah. But can we actually prove it? Yeah, you can do that in mathematics, but I'm just going to give you a simple proof here. So we know that the rate law is written as rate is equals to rate constant reactant A raised to the power 1. Okay, because it's a reactance, right? Your rate can be defined as minus dA dt. Okay, and this is actually equals to K A. At this stage, you might not have learned the mathematics, but this is actually known as an ordinary differential equation. So you can actually perform an integration, okay, by a method known as variable separable. Okay, so if you do that, right, I'm going to bring the A term to the left, the dt term to the right. So I'm going to end up with 1 over concentration of A dA equals to minus K dt. I'm also bringing the minus sign to the right hand side. The reason why I'm doing that is because I just want to ensure that the A term overlaps so that I can perform an integration over here. So when I perform an integration, right, I will actually integrate from time equals 0 to time equal t. And at time equals 0, I have A naught. At time equal t, I have A. So when I perform an integration, I'm going to end up with ln A, concentration of A. And then, of course, the limits would be A naught to A. Okay? And then this is actually equals to minus KT. Right? And then if you just subtract them, you are going to end up with ln A over A naught equals to minus KT. Yeah, I think from here you can see that the concentration of A is dependent on A naught and then e to the power minus KT. Yeah, so this is actually an exponential decay, and you can easily use this to prove the half-life is actually equals to ln 2 over K and is independent of the initial concentration of A naught. Yep. Okay, so with this equation, we can start by doing some mathematics. I know this is a long method, but I think it is worthwhile looking at it to convince yourself that, you know, this is indeed true. Okay, yeah. So, so we're just, okay, first we look at G, okay. So for G, right, we can look at G as in the concentration is equals to 4x. Okay, for x e to the power minus kgt, and then for h equals to x e to the power minus kh t. Okay, then of course here we define at time t. Okay, both will be the same. So in that case, at time t, 4x e minus kgt is equals to x e minus kh t. And you know that x can be cancelled off. Okay, and of course here you know what is kg. You can easily work that out because we have this particular equation. So in this case, we have 4 e to the power of minus, so what's kg? That's ln, okay, we can find out from here, that's 5 minutes, so ln 2 over 5t, and this is equals to e minus ln 2 over 15t. Okay, and then we can take ln on both sides. I'm going to end up with ln 4 minus ln 2 over 5t, and this is equals to minus ln 2 over 15t. Okay, so I'm going to shift the variables around. I'm going to end up with ln 4. When I shift ln 2 over 5 to the right hand side, we can just multiply by 3 top and bottom. So we get 3 ln 2 over 15. So that's 3 ln 2 over 15 minus ln 2 over 15. So I'm going to end up with 2 ln 2 over 15 t. And then you know that 2 ln 2 is actually ln 4. So we can cancel this off and we get t is equals to 15 minutes. Okay, so that's how we can prove it using mathematics. But you realize that for proving using mathematics, right? The half-life, I can give any half-life to any of these two, and eventually you will end up with a number. The number need not correspond to any of the half-life of the two species. Yeah. So you notice that for the limitation of this question, right? The limitation of this question is that I need to give you beautiful numbers. Do you notice? I need to give you beautiful numbers that is kind of like a multiple of the other one, so that you can easily solve it. If I'm going to give you, like, let's say the half-life of G is 5, the half-life of H is, let's say, 8, within what you know, it's difficult to solve without mathematics. Okay, yep. So if you're interested in using Excel, I can also show you. Well, this is an online debrief, so I can just show you some of the interesting things that you can be looking at. So let's say I'm going to type G, okay, and H over here. Okay, so maybe I'll just centralize both first. Okay, G and H. So let's say I begin with 80 G. Okay, and you know that H, because it's given in the question to be 4 times, you have 4 times more of G as compared to H. Yep, so I can just divide. I can just give a random number, right? And then I can just input the half-life as well. So I can just put half-life. Okay, so let's say the half-life of G, it's given to be 5 minutes. So I'll just put a 5 and 15 here. So again, let me just centralize them to make it look nicer. Okay, 5 and 15. And then what I'm going to do now is I'm just going to create the formula. Okay. So what kind of formula am I creating? Remember, earlier on we had this exponential decay formula. Yeah. So I'm just going to create this formula to solve it for you to take a look. So I think it will take a bit of time because well, I'm still quite still trying to do this recording, so I think it takes a bit of time. So let me just try to do it fast. So T, G, and H, okay, over here. And so let's say I give you a timing 0, 1, 2, okay, so I'm going to drag it all the way down to maybe 15, okay, and then the amount of G that remains, okay. But before that, maybe let me calculate a rate constant first. Let me just calculate a K. Okay, I think it might be easier. So the rate constant of K for G will be equals to ln 2 divide by the T half. Okay, so that's this particular number, and I'm going to do the same. Okay, so yeah, so these are the two numbers I'm going to create. Okay, and then right now I'm going to input my formula. Okay, so this is okay, so remember earlier on, this is the formula. Concentration at any timing is actually equals to the original concentration exponential e to the power minus kt. Okay, so I'm going to do the same thing. So this is equals to the original concentration, okay, multiply by exponential e minus kt. So k is this, and then I'll multiply this by the time. Okay, so I'm going to close bracket. All right, so I'm going to get obviously it's going to be the original value, okay, but I'm going to change the formula a little bit because you know that the original concentration or original amount of the numbers is actually a constant, so I'm just going to make it a constant, and then the rate constant is a constant as well. Okay, so I'm going to just drag it down, okay, to this. Okay, so this is what I'm going to get. Okay, and then I'm going to use the same formula. Okay, again, I'm just going to change the formula a little bit. So this will be 4, and then this will be 4 as well, and then C. Okay, so I'm going to drag all the way down. Okay, and bingo, you see? So this is exactly what we're talking about. Okay, so if you are more of a graphical person, then we can actually do a chart, and then you can see that it actually crossed at 15. Okay, then of course, some of you might be wondering, hey, I mean, you're looking at beautiful numbers, like it's not realistic, right? Okay, yeah, so beautiful numbers definitely, I mean, you might not think that it actually represent reality lah. Yeah, but we can easily change the half-life to non-multiples. Remember, just now I was saying if I change the age to 8, yeah, you're definitely not going to see them crossing at nice numbers. Okay, so you can see that they cross at some point which is a little bit difficult for you to actually phantom. Actually, they might not even cross much. Okay, so okay, maybe I change it to 13. Okay, so you can see that the crossing is not a nice number, right? Okay, so even if I drag it down all the way to 18, all the way to 20, you can't do that. Okay, so you can only use the mathematical method to solve this. Okay, or you can use the graphical method. So if I just show you these two graphs, you're going to see them crossing at one point. Okay, so I'm just going to drag it a bit so you can see. Okay, so yeah, so they're going to cross somewhere here. Yeah, which kind of like reflects a little bit of the reality, I guess. That's between 13 and 14, right? Yeah. Okay, yeah. So if you solve the mathematics, you can get an exact solution. Okay, but if you don't do the mathematics, you can't solve it. So that also means that for this particular question, right? If I'm going to change the question to 5 and let's say 13 or 12, you can never do it. You will never get a nice number. Okay, maybe you will get an approximate number, but it will not be a nice number. Yeah. Okay, so my apologies. I spent a bit of time looking at this because I thought that it's interesting to show you how you can use mathematics and even Excel, right, to actually solve a problem like this. Okay, so we'll move on to question 3. I think it reads, which graph would confirm the rates of decomposition of hydrogen peroxide first order? So I think this is very, very clear cut because we are looking at rates against concentration, right? So definitely a straight line that passed through the origin. So I think there's nothing to argue about this because the rate is directly proportional to the change in concentration. Okay, so question 3 will be C. Okay, so we're going to move on to question 4. So for question 4, right, you have the rates of decomposition of azomethane is studied by monitoring the partial pressure. Okay, so again, we monitor it by looking at the partial pressure here. So that's the partial pressure of azomethane. You can roughly see that it begins with about 30. Okay, so this is a important number that you might want to take note of. Okay, so then after that, if you look at the question, right, they ask you to actually use the half-life method. Okay, we use the half-life method to deduce the order of reaction with respect to azomethane. Okay, so okay, so I think the first thing we can do is maybe we'll zoom a little bit in. we have 30 here, so we probably look at 15. So 15 is okay, so I'm going to make it final. So 15 is around here. Okay, so this particular coordinate, yeah. So if you look at the x-axis, that's about 11, 12, maybe around 12.25, maybe. Okay, so that's like 12.25, 15.0, thereabouts. And then can we halve it again? We cannot halve it again because we don't get any values at 7.5. And please do not extrapolate. Okay, please do not extrapolate. You're not supposed to extrapolate. Okay, so the first half-life is actually 12.25. Okay, we cannot get consecutive half-life, so maybe we look at other possible combinations. So maybe we look at from 20 to 10. So we try to look at this maybe. So that will be, let's see what's the value. That's 5, 6, 7. So that's about 7.25, 20.0. And we try to look at this. This is maybe about 19, but it hasn't hit 19, so that's about 18.75, 10.0. So if we take the difference between 18.75 and maybe 7.25, I think we get about 11.50 thereabouts. Okay, so that's yeah, so that's about one of the half-life we can get. Okay, of course, if you don't want this, you can look for 25, and 12.5 is really up to you. Okay, so if you choose, you can see 25 here if you want. I mean they are really I mean, you can get as many half-life as you deem fit. Okay, so you can get about 25 here. So 25, I think it's kind of like smack right in the middle. So that's like 3.25. Would that be that's 3.25 and 25. And then if you want, you can that's 12.5, right? Okay, we just have a point here. So that's 15, 12.5. So maybe this is nice. So 15 minus 3.25. So the other t half. So our first t half we get is about 12.25 minutes. The second t half we got just now was 11.50 minutes. Then the third t half we get is 15 minus 3.25, that's 11.75 minutes. Yep, so it's really up to you. Like like you have a lot to choose from. Well, I mean, if you ask me, what so how? So during exam, I mean, the half-life is not exact. What you can do about it? I think my comment to you is actually it doesn't really matter here. Like we will mark it based on your working anyway. So in this case, I just want to have simple numbers. So I'm just going to get 12.25 and maybe 11.75, so that the numbers is maybe a little bit easier for me to work with. Yep. So in that sense, we will say that okay, the t half is relatively constant. Can we say that? So t half relatively constant. Okay, at around 12 minutes. Okay, we do this by taking an average. Okay, relatively constant at about 12 minutes. Okay, so therefore this is how we confirm that it's actually first order kinetics. Okay, then the next part is we are supposed to write the rate equation for the reaction. So calculate the rate constant giving its units. So that's that will be quite straightforward. So the rate constant in this case will then be rates is equals to K azomethane. So we can just put azomethane to the power of 1 because it's actually a first order reaction as shown seen what I mean as shown here lah. But then some of you might be wondering can I leave it in concentration or must I leave it in partial pressure? Okay, so in this case the question didn't really mention, so I can leave it in either concentration, or if I want to I can actually leave it in partial pressure. Yeah, but partial pressure might work a little bit better here. The reason is because the variables or the parameters we are given is in partial pressure. So maybe leaving it in partial pressure actually makes a little bit more sense. Okay, so yep. So we have this, and then you are asked to calculate the rate constant. Okay, so I think this is quite trivial because in this case you get the rate constant is equals to ln 2 over t half. Okay, and we found that the rate constant earlier on I just took the average about 12 minutes, so it's 12, so I can easily calculate this to be 0.0578 per minute. Okay, some of you might be wondering, should I leave my rate constant in per second or per minute? As I said I mean the timing here is given as minutes, so just leave it as per minute. I think it is fine. Okay, and then finally you are asked to calculate the time required for the partial pressure of azomethane to decrease to 3.75 kilopascal. So again, there's an easy way to do this, and there's a difficult way to do this as well. So we can do this by looking at the initial partial pressure, which is 30.0. So initial partial pressure 30.0, so we can just do 30.0 reduce to 15.0, reduce to 7.5, and then reduce to 3.75, and then we just determine how many half-life have we gone through. So that's 1, 2, 3. So that's a total of 3 half-life. So therefore time taken will be equals to 3 times 12.0, so that will be 36.0 minutes. Okay, so yep, so that's one way we can do it. And of course another way you can do it is, remember we have painstakingly derived this for you earlier on, right? So this is the exponential decay. So yep, since we have derived this, then you can easily make use of this. So 3.75 is equals to 30, and then E minus I mean the rate constant. I mean this is the rate constant, so I can just easily minus ln 2 over 12, and then t. So you can solve this. So you can easily solve this expression. I think you should be able to get 36.0 minutes as well. Okay, yep. So that's the end to our debrief for our in-class exercise. So please look out for the next debrief for in-class exercise 2.